It's got nothing to do with what came before. The connecting thing is derivatives, of course. We are going to be looking at what are called indeterminate form. We are going to find ways to find the limits of unusual functions, basically fractions. And the first term that we're going to try and get used to is what's called indeterminate form. These are limits that when you try and get the answer, the calculation that you're left with, you don't know the answer. So can you imagine you did a question where it was a limit and you plugged it in and you got 0 on the top and 0 on the bottom? You do not know what that is equal to. It is not equal to 1. 7 over 7 is equal to 1, right? 40 over 40 is equal to 1. But 0 over 0 is called indeterminate form. It means we do not know yet what it's equal to. So you want to imagine that this came from the limit of something divided by something, and you ended up getting that. Infinity over infinity is also indeterminate form, right? Some infinities are bigger than others, so you can't tell the answer. And 0 times infinity is also indeterminate form. A lot of people think of infinity as a number, and when you start thinking of it as a number, you get the wrong idea. 0 times infinity could be 42. It could be infinite, and it could be 0, because infinity isn't a fixed value, right? It could be as large as possible. So even 0 times infinity doesn't necessarily guarantee that it kills it. Of course, there are other combinations of zeros and infinities and numbers that we do know the answer to. What would 0 over infinity get you? Here's a number. What would 0 over infinity get you?
0.
In fact, in a way, isn't that like 0 with steroids, right? It's really, really 0, right? Infinity divided by 0 would get you infinity. So that's not indeterminate, right? If you know what the answer is, and infinity counts as an answer, then it's not indeterminate. What about infinity times infinity? Kind of obvious, I hope. What would that get you?
Infinity. And
0 times 0 gets you 0, right? Now you can do zeros and infinities in some combinations at least. 0 and 10, nothing special about that, 0. Isn't infinity divided by a number like 17 infinity? Isn't 13 divided by infinity a number?
Yes.
And?
0.
0. So are we comfortable in our head what an indeterminate form is? There are not many of them, right? There are not many combinations of zeros and infinities where you don't know the answer, right? There are quite a lot of combinations where the answer is known, right? If I said, what's this? You could say it's infinite, right? For example. So let's show you what Lhospital discovered. Really clever guy. I believe he's a Belgian mathematician. And he says this: if the limit as x tends to a of some fraction f of x over j of x is indeterminate form. In other words, it ends up looking like these guys, right? If it is, he found out that the limit as x tends to a of f of x over g of x, you can find that limit by finding the limit as x tends to a of the derivative of f over the derivative of g. Now that is not the quotient rule, right? The quotient rule has f dash g minus f g dash the whole lot. Isn't that just the top guy's derivative divided by the bottom? Is that not amazing that the limit of this fraction is the same number as the limit of that fraction? It's called Lhospital's rule. When you use Lhospital's rule, you normally put a little L above the equals so that people know what the heck you've just done, right? Let's take an example of how that would work. let's suppose I wanted to find the limit as x tends to 3 of x minus 3 over x squared, take away 9. Now, we have other methods to do that, but let's pretend we didn't know about those methods. The first thing you would do is you would plug in 3. And that would be 0 over 0. Would you agree that is one of the indeterminate forms, which means you can now use L'Hopital's rule, right? 0, 0, right? Then the limit then, as x tends to 3, of x take away 3 over x squared take away 9 is the limit as x tends to 3. If you differentiate the top, you get 1. And if you differentiate the bottom, you get 2x. And now you can plug in 3, and the answer is a 6th. So the original question, we didn't know what the answer was, right? Indeterminate form. But if you do L'Hopital on it, you get that. So far, so good. Nice little niche market. Let's pick this fella. I'll do it on the new page. So let's find the limit as x tends to pi upon 4 of cosine x take away sine x all over the tan of x take away 1. Now, if I plug pi upon 4 into each of these guys, you get root 2 over 2, take away root 2 over 2, so that's 0 on the top. The tan of pi upon 4 is 1, so 1 take away 1 gets you 0 on the bottom. 0 over 0, right? Indeterminate form. That means I can use L'Hopital on it. So it's going to be the limit as x tends to pi upon 4. Now, if you differentiate a cosine, you get a negative sine x. If you differentiate a sine, you get a cosine x. So that's what the top looks like. Okay, cobweb time. What's the derivative of tan x?
Secant squared x.
Nailed it. Now, putting this over here, I'm now going to plug pi upon 4 into stuff. So it's going to be that guy, take away that guy, all over secant squared of that guy. Right? If you get, if I got it handy, probably, oh God, would you believe it? I've actually does have it handy. If you use your unit circle, the sine of pi upon 4, here's pi upon 4, is root 2 upon 2. So it's negative root 2 upon 2. The cosine is also root 2 upon 2. And if you want to find the secant of pi upon 4, you find 1 over the cosine of pi upon 4. That's the easiest way. So I'll find the cosine of pi upon 4, which is this guy, right? And then 1 over it basically means you turn it upside down. So it ends up being that guy. And then I square it, because that's just a secant. This guy and this guy, so you've got a half and a half, gets you negative root 2 when you combine them. This guy gets you 4 over 2, 2 squared, root 2 squared. That guy over 2. There is the answer to this limit. It's negative root 2 over 2. You could not do that limit until we showed you L'Hopital. Remember way back in week 1, factor and cancel, right? That was one of our techniques. What else did you have? Conjugate rule. Well, that wouldn't even be a starter on this case, right? And then brute force, just plug the number in. So we now have a way of finding limits for fraction functions that are a little bit different than before. Suppose I want to find the limit as x tends to 0 of the tangent of 2x over the sine of, 3x. Right? If you plug 0 in here, tan of 0 is 0, sine of 0 is 0, indeterminate form. Lhospital's rule. The limit as x tends to 0. If you differentiate a tan, you get a secant squared of 2x. But isn't this a chain rule? So it's not just the secant squared of 2x. Don't we finish with the derivative of the inside function? So that's an extra 2. Now this fella, if you differentiate him, right, you will get the cosine of 3x times an extra 3. And now I should be able to plug in 0. 2 times the secant of 2 times nothing is still nothing. 3 times the cosine of nothing. And the cosine of nothing is its x coordinate is 1. So 3 times 1 on the bottom. You wanted secant. Well, isn't the secant 1 over cosine? So you just get 2 times 1 squared. And there you go. The limit of that guy is 2/3. Wouldn't this have been a really cool method to do in week 1 when you were doing limits? Problem is, you didn't know how to find derivatives in week 1, did you? Right, it took, what was it, week 3, we finally got around to doing those guys. You can also use Lhospital when the limit is infinity. So the limit as x tends to infinity of x plus x squared over 3 take away 5x squared. If you plug infinity, you get infinity over some kind of infinity in the bottom. It's definitely indeterminate. So I'm going to use Lhospital. You get 1 plus x and nothing, and you get negative 10x. Now, if you plug infinity into here, you get something like infinity over negative infinity. Would you agree it's still indeterminate? I don't know what infinity over infinity is. Well, you might think, oh, well, I guess Lhospital doesn't work for everybody. But it does. What do you think I should do? I want to find the limit of this. What do you think I should do? Do it again. If you differentiate the top, you get 1. If you differentiate the bottom, you get negative 10. Hey, there you go. So Lhospital can be repeated as many times as you want until you get to a point where you actually have an answer, right? That's kind of helpful. Let's put a weird one in, although most of them are pretty weird. Let's do the limit as t tends to 0 of 4 to the power of t, take away 3 to the power of t over t. 4 to the 0 is 1, take away 3 to the 0 is 1, 1 take away 1 is 0, 0 on the top, 0 on the bottom, indeterminate form. So it's going to be the limit as t tends to 0. Now, differentiate t, you get 1. If you differentiate 4 to the power of t, what do you get? What's the derivative of 4 to the power of t?
Didn't just 0?
Nope. 4 to the power of t. Right. Side issue. If I said to you, find the derivative of e to the t, isn't the answer e to the t? And we did a guy called a to the t. Actually, I probably would have called it a to the x. And you do get a to the t, but what else do you get? There's an extra little guy that you get. Can you remember what that little guy is?
I used to stick up joints like this. What an example you said.
Not sure if that was someone answering or talking to someone else. Anybody find it? Nobody got it? Yeah. Anybody feel like they are lucky and want to guess? Do you get that guy? Or do you get that guy? Which one do you get? Okay. I'm just going to dot that. If I tell you right now, evidently, because I did it last time, it went in one ear and out the other. You never remember it. So I'm going to give you the job of finding it out, because if you find it out, it'll probably stick in your head. If I just tell you, you're just going to say, oh, okay. You know, tomorrow I can ask you and you'll not remember again. Some of these guys you just have to have in your vocabulary. You just have to know what they are. You can't go looking up things like that. It's not a good strategy for success. Okay, so this one I am going to do, because you are all going to cheer me up here. Because these are not difficult to integrate, differentiate. Right, differentiate this guy, you get e to the x. If you differentiate e to the negative x, you get e to the negative x. Do you get anything else? If you differentiate e to the negative x. Chain rule, e to the negative x. I didn't catch that.
You multiply by the negative one.
Negative one.
Yes, agreed. Negative one. I think it may be my mic. It's not making my life easy today. You get that. Now, if you plug 0 into this expression, you'll get e to the 0, take away e to the negative 0, still 0. And you'll get e to the 0, take away 1. So what you're going to get here is, oh, indeterminate form. Well, when that happens, you just do it again. And you differentiate this guy, you get e to the x. If you differentiate this guy, you get negative e to the negative x times another negative 1. So it now becomes that guy. And you differentiate the bottom, you get this guy. But now you can put in zeros. And the answer is 2. You like that guy? Let's try some more. Oh, some interesting ones still to do. And it's a 3x, take away the sine of 3x, and it's a 3x, take away the tan of 3x. If you put in 0, oh, have you noticed I've got a little plus on it, 0 plus? That just means it's a right-hand limit. Right, weak one, right, left and right. Does it make any difference? Not one iota. It's just to keep it legal. Right, so pretend it's 0 and you'll be fine. Now, if you put 0 on the top, the whole thing on the top ends up being 0. If you plug 0 into the bottom, so does the bottom. So indeterminate form, we can now do Lhospital. That guy gets you 3. If you differentiate the sine of 3x, you'll get the cosine of 3x times another 3. If you differentiate that, you get 3. If you differentiate the tan of 3x, you will get secant squared of 3x times a 3. Now, if you plug 0 into that, can you trust me, it ends up being indeterminate again. So I do Lhospital rule one more time, or maybe 2. If you differentiate this guy, you get positive, because 2 negatives give you positive, 3 sine 3x times another 3, so you get that guy. And then you get a really messy answer on the bottom. So I'm going to do that in a separate piece of paper. I want to differentiate that guy. I'm going to column that guy. So you want to differentiate this. That gets you 0. Chain rule, multiply by 2. And then you differentiate the secant of 3x, right, the inside function. The derivative of secant 3x is secant 3x times tan 3x times the derivative of 3x, which is times 3. So you end up with negative 18 secant of 3x squared tangent of 3x. And that ends up being negative secant squared tan 3x. Wow, it's messy. Let's put it together. And I've got this fella, and then I've got negative 18 secant squared 3x tan of 3x. Put 0 in, I get 0 on the top. Put 0 in, I get 0 on the bottom. Evidently, I have to do it one more time. And I'm not that happy that I have to do it one more time, but I'm going to get 27 cosines of 3x. And that horrible mess is going to be a product rule. And I'm just going to put dot, 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 dot there. And the answer you will get eventually is 27 over 54, which is a half. And that you're going to have to trust me on. So that's one of the last questions. So what that is saying is that sometimes when you do Lhospital rule, don't you just have to keep going until you get an answer? Right, and it might take you more than you think. I didn't think that was going to take me 4 thoughts, but it did, right? So you got to hang in there when it's that case.
So I have a question.
Yes.
So when you're using this rule, that means that there is always an answer? Like always?
Yeah, always an answer. Now, it hasn't harmed
Okay.
you. Sometimes you might talk yourself out of an answer. Can you imagine that I did it and I end up with 0 over infinity, right? That could happen. But isn't the answer to that 0? Can you imagine a question where I might get infinity over 1? If that happens, it's infinity. So normally when you do it, you get a number on the top and a number on the bottom, right? And Lhospital's rule basically will allow you to find the limit of weird and wonderful fractions, right? So if you keep going, eventually it will do something. They're not going to give you a question where the answer doesn't exist, because that's just not fair, because couldn't you keep going until you retire, right? There's nothing to stop you differentiating one more time, right? You can always differentiate. So you have to know when to stop. Hopefully you realize that each time you do it, you do a quick check to see if the answer's, 2 numbers, or whether it's 0 over 0 or infinity over infinity. Are we good? Right, now, that is Lhospital's rule, as far as I'm concerned, the gist of it finished. So now I'm going to tell you some special cases. And the first one is just because you can doesn't mean you should. I've used that rule in lots of situations. That rule does exist in Lhospital's rule. Here's two examples of this rule. First one. Suppose I asked you to do that limit. Now, if you don't check by plugging in 3 and making sure that you actually have an indeterminate form, you could say, well, don't bother checking, just use Lhospital. Watch what happens if I use Lhospital. You differentiate the top, right? And you differentiate the bottom. And now you plug in your number, and what do you get? 6/3, you get 2. So, hey, I got an answer. That must be the limit, right? Let me check that one. It would be me doing that, wouldn't it? Oh, here we go. 3 squared plus 9 over 3 times 3 is 9 plus 9 over 6. It's 18 over 6. Isn't the right answer 3? So if you're saying, I wonder why you kept on doing that check that it's indeterminate form. Do you know if you just keep going because you want to, and then you just stop after the 4th one because it seemed like a good idea, couldn't you overshoot the answer and get the wrong answer? So just because you can doesn't mean you should. So yes, I could use theoretically Lhospital, but I shouldn't. Agreed? So watch, it's a possibility. That's the first special case. Second special case is, suppose I wanted to find the limit as x tends to 3. Something like that. It has a square root in it. If you plug in 3, it is indeterminate form. All right. Actually, yeah, that one would work, but I've just thought of a better one. Yeah, that one. That would also work. I could do Lhospital on both these guys. They're both 0/0 indeterminate form. If you do any kind of derivative involving square roots, doesn't the answer get really ugly really quickly? That one would be much better. Use the conjugate method. If you do Lhospital, especially if there's more than one square root, all that happens when you do a square root is, don't you get x to the -1/2 and you get weird fractions with square roots in them, and then the next one is even worse than the one you just did, and you keep going forever and it really doesn't stop. So be careful. If you see square roots involved, think of doing week 1, week 2 stuff, right? Think a Lhospital is not the choice, but think of a conjugate method. So that would be my second special case. And my last special case is you can use Lhospital in questions that don't have fractions. Here's an example of one. I would like to know the limit as x tends to 0. Well, if I plug in the numbers, it's 0, the natural log of 0. Can you trust me that if you do a log function, the log of 0 is minus infinity? Would you agree that's one of those indeterminate forms? Nobody knows what 0 times negative infinity is. But you can do L'Hopital rule even when it's multiplications. You just have to be a little bit sneaky. And this is how the sneaky part works. You make it a fraction. Would you agree that x log x and this weird fraction are the same thing? If you want to see what the intermediary stage looks like, there. Does it look more like it now? Right. So let's use that form because that seems to look easier in people's minds. If I do L'Hopital on it, if you differentiate a log, you get 1 over x. If you differentiate x to the -1, you get negative x to the power of x minus 2. If I do some algebra on that, it's 1 over x, negative 1 over x squared. If I then do a little bit more algebra on it, it's 1 over x divided by that guy, which is 1 over x times that guy. The x's cancel, and you're allowed to do that. And what we now have is a limit as x tends to, actually, there'd be a plus on this, but that's only to keep it logical. You'd get negative x, and negative nothing is nothing. So x log x, the answer is 0. The limit of x times log x is 0. So just because you can, right, doesn't mean you should. If you see square roots, don't even think about doing L'Hopital. Algebraically, it's horrendous. So I suggest don't. And you can even use it for things multiplied. So a nice little trick, right? Uses derivatives, allows you to get limits. It's good for what it does. It doesn't do anything else, but that's what it does, and that's good. Any questions about that? Because we're going to move on. Well, I said that, and then I realized there's one group of questions not really using L'Hopitals, but testing, do you recognize indeterminate form? So here we go. Are you looking at question 1 here? WebAssign question 1. Can I see a nod or a shake?
Yes.
Okay, we're good. Right. You are told what all these, the limit of f is 0 and g. So if somebody said, is this indeterminate form, right, or not? Right? If the limit is indeterminate, enter indeterminate. So I'm wondering what you do if it's not. I guess you say not. This would be 0 over 0. Do you agree? 0 on the top, 0 on the bottom. That's indeterminate. I'll just put an I there, right? A capital I probably better. What about f on the top, p on the bottom? F on the top is 0, p on the bottom is infinity. Oh, wait a minute. If you do 0 over infinity, Okay, it's a bit messy here. Guess I can find it. Where are you hiding infinity? There you go. 0 over infinity is not indeterminate, is it? What number is 0 over infinity?
Zero.
0. So now I know what you write down. When it's indeterminate, you write indeterminate. And all the other times, you write 0. Right, here's another bunch of them. Couple of them are zeros, F and G. Couple of them are infinities, P and Q. And H has got a limit of 1. So this first one would be P times Q. Would you agree 0 times infinity is indeterminate? Right? 0 multiplied by infinity, indeterminate. What about 1 multiplied by infinity? Right? H is 1 and P is infinity. What would 1 times infinity get you? That's not indeterminate.
Infinity.
Right, infinity. And you type infinity. Do you feel comfortable that if we tell you what the limits of F, G, P, Q, R are, that if I gave you any multiplication or division combination, that you would feel comfortable about indeterminate form? Right. There, that's the little guy I went and missed. So now I haven't missed it. So we're moving on to, for this week, our final section. Give me a few moments to load it up. While I'm doing that, why don't you put down your last name for attendance? Give me a chance to get this set up. Okay, I'm ready now. We are going to use calculus to help us sketch some curves. Now, they're going to be, and don't fall into this temptation, there's going to be a temptation that you're just going to plug it into Desmos, and whatever Desmos tells you is the answer. And if you fall into that temptation, you're going to have a problem when we do the final. Because in the final, I'll be expecting you to show me all the calculus and the algebra that you used to do the sketch. So I'm just going to do the shopping list of things that you need to buy to draw a curve. So you're going to have a function. I'm just going to pick one, which I think is question 1. It's a nice cubic here. And we are going to sketch that guy without Desmos, without any calculator, basically doing it through calculus. So first thing that you should do is you should look for the intercepts. So there's nothing new here because you did this in 141. There are 2 kinds of isn't there? There's where it crosses the x-axis, and they're called x-intercepts. And there's where it crosses the y-axis, and they are called y-intercepts. So far, so good. Now, in this case here, if you want to find the x-intercepts, don't you solve when is the function 0. So you're trying to solve when is x cubed plus 9x squared equal to 0. So if I pull out x squared as a common factor, which is typically what you would do with a polynomial at least, can you see that we now know that it cuts the x-axis at 0 and it cuts the x-axis at -9. Over here, I'll start my sketch. There's my x-axis, there's my y-axis. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow, looks like I'll need more room than I thought. Now, if you want to get a y-intercept, all you do is you find the value of the function at 0, which in this case is 0, which means, well, we already know what it means. It means it crosses the origin, right? Now, if this was x cubed plus 9x squared plus 5, wouldn't the y-intercept be at 5? Right, so you could get that. So that's your first job. And this we're talking about is how you would sketch polynomials. We have to tweak it for different curves, but for polynomials, this is what you do. Look for the x and the y-intercepts. Second thing that you now do is you find when it's increasing, decreasing, and max and min. You find those guys. When is the function increasing? When is it decreasing? But more importantly, you want these two things. Where's the local max? Where's the local min, right? So all of those you get from the first derivative. So I'm now going to differentiate my function, and that's 3x squared plus 18x. Now, if you want to find increasing, decreasing, max and min, right? You want to find all those things. Don't you now need to get critical numbers? Would you agree for polynomials, critical numbers are only going to happen when the derivative is 0. So we're trying to find when is this 0. So we're trying to solve that. Okay. Any ideas what I should do to the left-hand side to solve this problem? Think algebra. What could you do to this expression to find out when it's 0?
Divided by 3x.
Okay. Now I would pull out 3x as a common factor, which might sound like it's pretty much the same thing. But if you divide by something, you very often lose one of your critical numbers. So think factoring rather than dividing. In this case then, x equals 0 and x equals -6. And this is a duplication of what we've done in the past. Because all I'm going to do now is set up my table of values, because my table of values is going to tell me increasing, decreasing, and all the other good stuff. So I have a guy, so a space, -6, a space, that's a space, 0, a space. And I'm going to put in, I don't know, -7, and probably -3, and for no reason, 2, because I felt like it. We put in the derivative, we put in the shape. So I go to my calculator, I go y equals, clear this out. The guy I should be putting in is the derivative, not the original, but the derivative. So I'm putting in 3x squared. What did that do? 3x squared, that's better. Plus 18x. My table is already set up. I'll go here, delete the old stuff, and type in -7, -6, -3, 0, and finally 2. And I get 0 here and 0 here, which isn't a surprise. I get a +21, I get a -27, and a +48. And that gets me positive, negative, positive, and zeros here and here. And again, I draw a number line and I only identify the critical numbers. And in the critical numbers, the derivative was 0. And we put in a plus here, so all of these are plus, negatives in the middle, pluses at the end. Can you see increasing, decreasing, increasing? Can you see those? If you look at the two critical numbers, that's the only place that max and mins are going to live. In this case, it's positive, 0, negative. So that would be a local maximum. And that's going to happen at x equals -6. Okay. And at -6, well, I'll find out what the value is in a minute. I can get its y coordinate. And this guy here is down, along, and up. And that's a local min. And that's going to happen, that one I can do. That's going to happen at x equals 0, 0. So if I go to my little picture, I have at 0, 0 a local min. So I know that this curve is going to look like that, right? And at 1, 2, 3, 4, 5, 6, at -6, and I'm going to have to find the value of that. So here goes. In brackets, -6 cubed plus 9 times -6. I get the answer -2. What? That's a surprise to me. Something's, oh, of course, that explains it. No, it doesn't. Too late now. Run out of time. But my shape doesn't match what I'd expect it. If you put this together, would you expect that shape, wouldn't you? Right. For that to happen, I would need a guy up here. So maybe I made a mistake in calculating that. That might be my problem. But can you imagine I found the coordinates of that and I placed it? Would you agree we've got, whoops, shouldn't rush. Would you agree we've